Welcome dear students to presentation on compiler design. This presentation discusses the topic syntax directed definition of module 4. Let me start by recalling the first four phases of compiler. As you know, the first phase of compiler is lexical analyzer. The input to lexical analyzer is source language. Tokens are generated as output for this phase. These tokens will be fed to the next phase of the compiler, which is syntax analyzer phase, or another name of syntax analyzer is parser, which will produce the parse tree. This parse tree will be fed as input to semantic analysis phase, which will create the annotated parse tree or decorated parse tree. Decorated parse tree means each node of the parse tree will be having some more information which can be called as attributes. And this annotated parse tree is fed as input to the next phase of the compiler, which is called as intermediate code generator. The output of the intermediate code generator is intermediate code. So we can say that this module explains how parse tree can be converted to intermediate code. As we know, module 3 stopped with the creation of parse tree. Here, each node of the parse tree, we are going to associate it with attributes. Attributes are really part of grammar symbols. Each programming language construct is associated with attributes. So for translation, we have to evaluate the value of attributes. The value of the attributes can be computed based on some rules. Rules can be called as semantic rules. The semantic rules are associated with the context-free grammar production. So if we have a programming language construct, we can represent it using a programming context-free grammar. This context-free grammar, we are using the productions of context-free grammar. Associated with the production, there will be semantic rules. So on evaluating semantic rules, we will be computing the values of attributes, so that we can make the parse tree an annotated parse tree or decorated parse tree. There are two ways in which we can associate the semantic rule with productions of context-free grammar. One is syntax directed definition, another one is translation scheme. This presentation focuses only on syntax directed definition. Syntax directed definition means it is a combination of attributes and semantic rules along with the context-free grammar. Translation scheme is more procedural compared to syntax directed definition. That means it can be represented using programmatic statements. Besides the production, context-free grammar production, we are embedding programming language statements in translation scheme. On comparing both type of notation, syntax directed definition and translation scheme, we can say that syntax directed definition is giving a high level specification for translation. That means it hides most of the implementation details. Another important thing related with the syntax directed definition is that the order of evaluation is not required to be mentioned. There is no specific order. We can evaluate based on the requirement. But in the case of translation scheme, there the order is important. Strict order is to be followed for evaluating the semantic rule. It is more programmatically given, so we can say that it will show some of the implementation details. Conceptually, both of these notation schemes parse a token, it will build a parse tree, it will traverse the parse tree, it will evaluate the semantic rules to compute the values of attributes. After all, on creating an intermediate code, it means, as we know, all the phases of the compiler are related with the supporting unit, simple table management and error management unit. On generation of intermediate code, it can say some information to the symbol table. Also, it can issue some error messages if there is error. So conceptually, the translation can be explained as: initially, a token will be given. Token means a string consisting of terminals. This string can be parsed to construct a parse tree. Then as a next step, a dependency graph is to be identified, because each node of the parse tree is associated with some attributes. So what is the relationship between the attribute? That is to be identified using this dependency graph. After getting a dependency graph, evaluate the semantic rules to compute the value of attributes. Thereby, we are obtaining the translation for the token. So we can go to the details of attributes. Attributes means it is actually the information contained along the nodes of parse tree. Attributes can be either string, number, type, memory location, or whatever it can be. Basically, there are two classes of attributes: synthesized and inherited attributes. This is usually asked as a short answer in university question papers. So please note it carefully. The synthesized attribute is computed from the values of its children node. We know that it is a parse tree. Each node of the parse tree is associated with attributes. If the attribute value of a node is computed from the value of the attribute of its children node, we can call it as a synthesized attribute. Whereas inherited attribute, as its name implies, the value of inherited attribute of a particular node can be computed from the value of attributes of the siblings and parent nodes. So the difference between synthesized and inherited attribute is very important. Again, this slide shows the explanation of the annotated parse tree. A parse tree showing the values of attribute at each node is called an annotated parse tree. The process of computing the attribute value of the node is called annotating or decorating the parse tree. This is actually what we are expecting as the output of semantic analysis phase. Attributes. Consider the production A is alpha. Capital A is the non-terminal on the left hand side, alpha is on the right hand side. Alpha is a combination of grammar symbol. It can be terminal or non-terminal, or it can be terminal and non-terminal combination. When we consider the semantic rules for this production A is alpha, if you are given a function b is equal to f of c1, c2, etc. ck, where b is an attribute, c1, c2, etc. ck are also attributes. Here this function implies that we are computing the value of the attribute b from the value of attributes of c1, c2, etc. ck by applying a function f over the c1, c2, etc. ck. Associating with the production A is alpha, we can explain this as b can be either thought of as a synthesized attribute for the non-terminal capital A. Synthesized means the attribute value can be computed from the value of its children node. That means c1, c2, etc. ck are assumed to be the attributes of alpha. Or b can be considered as an inherited attribute, which is actually b is an attribute value of one of the child node, and c1, c2, c3, etc. ck can be the attribute values of its sibling or its parent node. Anyway, we can say that here b is equal to f of c1, c2, etc. ck implies that attribute b depends upon the attribute c1, c2, etc. ck. Next is synthesized attribute. This is very important term S attributed definition. We have already learned about synthesized attribute. Synthesized attribute means the value of attribute has been computed from the value of its children node. And also we have learned about syntax directed definition. It is shortly called as SDD. SDD means it is the way in which we are associating the semantic rules with the production. So if the semantic rules uses only synthesized attribute, we can say that it is an S attributed definition. So if SDD contains only synthesized attribute, it is called as S attributed definition. S stands for synthesized. This is very important. If a parser is having only S attributed definition, its attribute can be, its value of the attributes can be evaluated with a bottom-up traversal of the parse tree, starting from the leaves, working towards the roots. It is actually in post-order traversal. Next is an important slide. It's showing the example of an S attributed definition. That means a syntax definition with containing only synthesized attribute. This shows the productions corresponding to a calculator which can evaluate the expression involving star, plus and all. These are the set of productions we are already familiar with, but in addition to the E gives E plus T, E gives T, T gives T star F, T gives F, F gives E within bracket, F gives digit, we can see an additional production L gives En at the top. Here it is added such a production to show that after getting the expression followed by a new line, it is to be displayed, it is to be printed out. So L is a procedure which indicates that expression followed by a new line should be printed out. And whatever is written on the right hand side of the production is called as semantic rule. Semantic rule explains how the attribute val associated with each non-term is getting its value. For each production there is semantic rule. So corresponding to L gives En, the rule is print of E dot val. Whatever value contained in the expression attribute, that is to be displayed. E gives E plus T, the rule says that it should compute the val attributes associated with the E and T, and it should be assigned to the val attribute of E on the left hand side. One thing more is we have to notice is that E is occurring at both LHS and RHS. So you know, to distinguish between that, in the rule it is mentioned as E1 in the right hand side. Similarly, we can see the rules for the productions E gives T and the rest. Here we are assuming that start symbol does not have any inherited attribute, and also the digit is a token or is getting its value from lexical analyzer. Consider the next slide. It is an example of a parse tree for the expression 3 star 4 plus 5n. The result we are expecting from this expression is 3 star 4 12, 12 plus 5 17. Essentially parse tree will be drawn for this. Then after obtaining the parse tree, so the token here is 3 star 4 plus 5n, that is the input string. Then we have drawn the parse tree. After drawing the parse tree, the attributes value is to be computed. Here it is computed by performing a bottom up traversal, that is a post order traversal. Post order means left right road. So we have to reach the bottom leftmost node of the parse tree. So we will be reaching the F gives digit branch, and F gives digit, while we reach the node, its corresponding rule will be evaluated. So in the previous slide I have shown that F gives digit is having the rule F dot val is equal to digit dot lex val. So here the lexical analyzer is producing 3 as the token. So that will be assigned to the val attribute of f. And moving upwards, it will be computing the t gives f. That means the rule corresponding is t dot val is equal to f dot val. So t dot val is copying the val attribute of f. Then since it is the post order traversal, it moves towards the right. There also f gives digit. The second token supplied by the lexical analyzer will be 4 and f will be having the attribute val as 4. Then it will move upwards. It is now reached the root of that subtree, but the rule is t star f. So it will be evaluating the rule corresponding to that. That means the children nodes will be having the attributes will be multiplied and the result will be stored in the root node. Then moving upwards, it will evaluate a gives t and its value will be copied based on the rule. Then it will move towards the right side. Again the next token 5. Move upwards, t will be getting 5 as its attribute value. Then again it will move towards the root. So it is corresponding to the production a gives e plus t. The values will be summed up and finally it will go to the root of the parse tree and the 17, the result of the expression will be printed out. Next is inherited attribute. Inherited attribute means the attribute value is computed from the attribute value of the parents, or it can be from the attribute value of the siblings. Next slide shows an example of inherited attribute, the rules, semantic rules which will be evaluating the inherited attributes. This set of production actually shows a declaration statement. It can be explained with the help of a C programming language declaration statement. Consider int a comma b. Here a and b means they are variables. Both of them variables we are going to declare it as an integer variable. So here in the production, capital D stands for declaration. D gives TL and capital T stands for type, L for the variable. So int a b. Int a is int t, L stands for a. If int a comma b is the case, that is to be dealt by the production L keys L1 comma id. So for dealing with such type of declaration statement, this set of productions is necessary, and for each production it is associated with a semantic rule, and this semantic rule is evaluating the inherited attributes. Here L is having an inherited attribute L dot in the first rule, D gives TL. That means when we consider the example or comparing with the example int a is having the integer value for the type value. So L dot in will be getting its attribute. That means variable is getting its type from its t, the t on the left hand side of the L. So L is an inherited attribute which is inheriting its attribute value from its sibling, and considering the t gives real, t gives int, they are having the type attribute, they are getting the attribute from its child node, real and int, so they can be called as synthesized attribute. Whereas L gives L1 comma id, the fourth production, again there are also the L and L same in both LHS and RHS, so in order to distinguish between them, they are giving it as L1. So L1 comma id, there L1 is having an inherited attribute. It is inheriting the attribute value from its parent node L. L dot n. But in addition to that, a statement is there, add type of id dot entry comma L dot n. That indicates that when int a comma b, a and b are arranged as variables having an integer type value, it is to be indicated inside a symbol table. So for storing the information regarding that variables, type information regarding that variables in symbol table, a procedure will also be executed called as add type, which will makes the entry for the id along with its type, which is actually stored in attribute in of L dot in. Similar is the case with the L gives id to, that means int a. The case of int a, the a will be stored, and along with that the type of a, that is int, will be stored. So we can explain the same concept using an example, real x comma y comma z. Here also a parse tree should be drawn, and the next step is to evaluate the attributes. Here it is inherited attribute, so we have to evaluate based on its dependency. So d gives tl, the leftmost one is t gives real. It will be evaluated first. It is a synthesized attribute. Then d gives tl, the L is an inherited attribute, it is getting its value from the type. So L dot n is equal to t dot type. The t type is having the real, so it will be copied to L. Then coming to L gives L comma id, there it is inheriting the parent node, so it will be having the real value. Again going to this L comma id, again inherited attribute real. Then when coming to L gives x, it is similar to the rule L gives id. So on executing that particular branch, it will be also implementing a procedure code to enter the information regarding the x into the symbol table. That is, information is the real attribute for x. Then it will move towards the y, right side of the tree, move towards the y. Then it will add the information regarding y also into the symbol table. Then as a next step, z, it will z also, the information regarding z also will be entered into the symbol table. Then from this we can understand that for implementing syntax definition, either we can use dependency graph, or you can use S attributed definition or L attributed definition. The previous example for a declaration statement which is having inherited attribute is actually an example of dependency graph. S attributed definition is the example that we have already dealt with the desk calculator, which is having only synthesized attribute. So L attributed definition can be seen in the next slide, next presentation. Initially we can discuss more about dependency graph. Dependency means if attribute B depends on an attribute C, we have to ensure that the semantic rule for B is evaluated only after evaluating the dependent one, the semantic rule for C. And this dependencies among the nodes can be represented using a directed graph called dependency graph. This can be explained with the help of this algorithm and also with a diagram. Algorithm just explains that if C1 and C2 are two attributes, if C2 is depending on C1, we have to evaluate C1 first, so we have to draw an edge from C1 towards C2. It will be more clear if you observe this example. A is having attribute A, small letter a. It is actually computed from its x and y children. That is, for the production, A gives xy, capital A is having a small letter a, which is considered as the attribute of capital A, and small letter x and small letter y are considered as the attributes for x and y. So if f is a function over x and y, and after evaluating x and y, if it is assigning it to the small letter a, we can draw the graph like this. Both of the edges will be, arrows will be pointing towards a. So this is a dependency graph. If another semantic rule is x dot x equal to g of a dot a comma y dot y. That means x is depending on for its attribute on the a and y. Then it will be represented using both a and y will be pointing towards x. Another example is e1 plus e2 val attribute e dot val. e1 and e2, both of them are pointing towards e dot. Consider the example of dependency graph. This is similar to the previously discussed example, which is having inherited attribute for the declaration statement. Here, initially, id1, id2, id3, all values are to be entered by the lexical analyzer. After that, the pass tree should be traversed in bottom-up order. So DGIS TL will be evaluated first. That is, DGIS real will be initially evaluated. T is having its type attribute as real, and it is giving it to the rightmost child, that is L, and it is getting its inherited attribute real from the T dot type. After that, it is giving to its child L, then it is giving to its next child L, and sequentially it is performed. So this path can be shown as a dependency graph. So we have a token, we have drawn the pass tree, we have considered dependency graph. Then next is we have to evaluate the attributes on the path shown by the dependency graph. This evaluation can be based on a topological sort, because dependency graph is given, so we can perform a topological sort to obtain the values of the attribute. Topological sort means it is any ordering of m1, m2, etc., mn of the nodes of the graph, such that if mi gives mj is an edge, then mi appears before mj. That means the dependency should be considered before evaluating. Dependency graph is basically a directed acyclic graph, so dependency graph will be successful only if when it is no cycles. So after considering dependency graph, evaluate the semantic rules by performing some topological sort over the dependency graph. So this slide shows the result of topological sort over the dependency graph for the declaration statement real id1, id2, id3. So which will result in producing the translation of the input string. Here it is actually the value of the attributes real will be stored for each id1, id2 and id3 in simple table. Then there are different evaluation methods for the semantic rule. One method is parse tree method that we already discussed. Build the parse tree, build the dependency graph, perform the topological sort and evaluate. This method fails only if if the dependency graph has cycle. Another method is rule-based method. In this method, it is a static one. We have to analyze the rules at compiler generation time. Either you can do it using a specialized tool, or you can directly do it by hand. Then you have to determine a static order of evaluation and evaluate based on that static order. Another method for evaluation is oblivious method. There is no importance for semantic rule. We are choosing a convenient order and evaluating it. So this is the end of syntax-related definition. On summarizing, syntax-related definition is a notation for describing semantic rule along with its attribute as part of the productions of context-free grammar.